Good morning, students. Let's continue the session with the shapes of orbitals. Last session we discussed about the shapes of orbitals and we studied them as shape of s orbital as spherical, shape of p orbital is dumbbell, shape of d orbital is double dumbbell. Similarly, shape of f orbital was observed as four-fold dumbbell, which cannot be picturized on a two-dimensional board. Shape of f orbital is four-fold dumbbell. Means so many lobes will be there. Spherical means it is symmetric with respect to all axes. Dumbbell means two lobes can be seen. Double dumbbell means four lobes can be seen. And when it comes to the shape of f orbital, it is four-fold dumbbell. We cannot picturize it on the board. So many lobes will come like this. In this way. So we have to remember this as four-fold dumbbell in shape, which is very complex in shape. Now another point we have to recap here. Number of nodal regions or radial nodes for a given orbital NL. Orbitals are usually represented with this NL notation. Like last class we studied, first shell has 1s, second shell has 2s and 2p orbital, 2p sublevels. 2p sublevel has 2px, 2py and 2pz. You remember that 2px, 2py and 2pz. Similarly, third shell has 3s, 3p, 3d. 3s is only one orbital. 3p has px, py, pz, and 3d has dxy, yz, zx, x square minus y square and z square. Of course, x square, y square and z square. Right, in this way we have studied the types of orbitals under every subshell. S subshell has only one orbital, that is s orbital. P subshell has 3 orbitals. D subshell has 5 orbitals. And F sublevel has totally 7 orbitals. Now, each orbital has how many nodal regions? Number of nodal regions for a given orbital NL. In this, suppose if you are talking about 1s, this 1 stands for principal quantum number, S stands for azimuthal quantum number. We have to remember this notation even for the calculation of energy of orbitals also, which is coming in the next topic. So this notation, orbital notation, is NL notation. Whenever an orbital is given like this, number of nodal regions can be calculated as n minus L minus 1. Nodal regions are nodal surfaces like that. Suppose for 1s orbital, nodal regions can be calculated as n minus L minus 1. For an s orbital, L value is 0. So formula will be n minus 1. For a p orbital, L value is 1. So n minus 2 will be the formula. For a d orbital, L is 3. Means n minus 3. L is 2. For a d orbital, L is 2. 0, 1, 2. So the number of nodal regions can be calculated as n minus 3. And for an f orbital, L value is 3. So nodal regions is n minus 4. In that way we can study this. This is another representing. Actually this is the correct formula to find out number of nodal regions. For 1s it is 1 minus 0 minus 1. It is 0 nodal region. For 2s it is 2 minus 0 minus 1. 1 nodal region. For 3s it is 3 minus 0 minus 1. 2 nodal regions. Already we have studied this in the last session. Once again, let us recap this. For 1s, suppose this is the nucleus. This is a 1s orbital. For 1s orbital, there is no nodal region within the boundary surface. Within the boundary surface, there is no nodal region. So number of nodal regions are 0. For 2s, suppose this is the nucleus and this is first boundary surface and this is second boundary surface. This is actually 2s. Inside we can take it as 1s, right? Now, with respect to this nucleus, electron can be observed either at a distance of 1s or at a distance of 2s. Between 1s and 2s, have you seen, between 1s and 2s, there is a region where probability of finding electron is 0, psi square is 0. That region is called as a zero probability region. This region is totally called as zero probability region, also called as nodal region. So for a 2s orbital, there is one nodal region. Likewise, if you consider 3s, first order 1s, 2s and 3s. This is 1s, 2s and 3s. See, For a 3s orbital, totally 2 nodal regions are there. This is one nodal region, this is another nodal region. So like this, we can calculate the number of nodal regions, even the corresponding picture also. Let us apply the same principle for another orbital. Suppose, consider p orbitals. Number of nodal regions for a p orbital. So p orbital means p orbital starts in first shell or second shell. Again we have to consider this point. First shell has only one orbital, that is 1s. Second shell has 2s and 2p. So 2p, p orbital starts in 2p. So number of nodal regions formula is n minus l minus 1. General formula this is. If it is a 2p, as it is p, or for a p, for np, number of nodal region is n minus 2. It's the same thing. This is a general formula. This is a particular formula for a p orbital. So for a 2p orbital, number of nodal region is 2 minus, what is L value for a p sublevel? 1 minus 1, that is 0. Even this formula also, n value is 2, and for a no need to substitute anything again, 2 minus 2, 0. So don't get confused between the general formula and particular formula for a given orbital. See, I am repeating once again, number of nodal region for ns is n minus 1. For np it is n minus 2. For nd it is n minus 3. For nf it is n minus 4. This is also similar to n minus 0 minus 1. This is n minus 1 minus 1. This is n minus 2 minus 1. This is n minus 3 minus 1. Okay. This is a general formula, and this is general formula, and this is a particular formula for a given orbital. Now, what is the picture, orbital picture for this? So this region is first orbit region, which has only spherical s orbital. Second region has s and p. Suppose this is s orbital, and we have one more orbital, that is p orbital in this way. See, I am drawing this in this double dumbbell shape. It doesn't mean that electron is orienting in this way. See, this is a p orbital. Below this boundary diagram, within this boundary diagram, there is no other p orbital. There is no other p orbital. So, no nodal region. No nodal region for 2p. Once again, I am repeating. For a 2p, this is the first starting p orbital, below which there is no other p orbital. As there is no other p orbital, no nodal region is possible practically also for 2p. When it comes to 3p, see, this is the first boundary diagram, second boundary diagram, and third boundary diagram. Suppose this is third boundary diagram. Again, in every case we have to study all these things. First boundary diagram has only 1s. Second boundary diagram has 2s and 2p. Third boundary diagram has 3s, 3p and 3d. So as 3d we are not discussing at present. I am taking 2p which belongs to second shell, 3p which belongs to third shell. Now for a 3p, how many nodal regions are possible? See, between 3p and 2p, there is one nodal region. See, this total region is called as nodal region, where probability of finding electron is 0. Next, theoretically, this is the picture. Formula based determination is number of nodal region is equals to n minus l minus 1. N minus l minus 1 is equal to, for 3p, n is 3, and for a p orbital anywhere it is 1 minus 1, 3 minus 2, 1 nodal region. Or number of nodal region for 3p equals to 3 minus 2, 1. So this is general formula determination. This is formula for a particular orbital. For a p orbital, n minus 2. For an s orbital, n minus 1. For a d orbital, n minus 3. Don't neglect these points. These points are very important for competitive exams. Next, like this, for a 2p, 3p we can compare. And similarly for 3d orbital. See, 3D starts in D, the third main shell. 3D starts in third main shell. So first, second and third boundary diagram, here d orbital starts. First d orbital starts in 3D. Below which there is no other d orbital. This is the starting d orbital. That's why for 3D there is no nodal region possible practically. And when it comes to, so nodal regions for 3D, formula is 3 minus 2 minus 1, 0. Or nodal regions for 3D equals to, for a d orbital, what is other formula? Direct formula, 3 minus, for a d orbital, 3 minus 3, it is 0. In either way, it comes as same. So nodal region for 3D is 0. When it comes to 4D, first boundary diagram, second boundary diagram, third boundary diagram and fourth boundary diagram. One d orbital is possible in third boundary diagram, another d orbital is possible in fourth boundary diagram. See? Now between this 3D and 4D boundary diagram, there is one nodal region where probability of finding electron is 0. This is the nodal region for 4D. So this is theoretically using a picture. Then how do you find it using a formula? Nodal region for the 4D equals to 4 minus, what is L value? 2 minus 1. It is one nodal region. Or nodal region for 4D, for a d orbital, what is the formula? N minus 3. 4 minus 3. It is 1. Okay, this is how we can calculate number of nodal regions when an orbital is specified. Now, when it comes to the next topic, that is energy of orbitals. Energy of orbitals, suppose NL is an orbital, then its energy of an orbital NL depends on its N value and L value. It is given as N plus L. Suppose if you consider the first shell which is closer to the nucleus, suppose this is the nucleus. This is the nucleus. Then immediate shell is 1s. 1s is the immediate shell possible, that is nearer to the nucleus. Then its energy can be calculated as, you have to remember this point, L is equals to 0, 1, 2, 3 sub-energy levels means SP, DF sub-energy levels. They are the designations and the corresponding symbols. Don't neglect this, very very important. Now for 1s, energy is 1 plus 0, it is 1. For a 2s, next is the second shell has, see, yesterday's class is very very important. Without that session, without knowledge of that session, you cannot follow this here. Its second shell has 2s, 2p. Third shell has 3s, 3p, 3d. Fourth shell has 4s, 4p, 4d, 4f. Fifth shell has 5s, 5p, 5d, 5f, 5g, etc. In that way, the number of shells in an nth shell is equal to n. First shell has one subshell. The second number of subshells in an nth shell is equal to n. First shell has only one subshell, S subshell. Second shell has two subshells, 2s, 2p. Third shell has three subshells, 3s, 3p, 3d. Fourth shell has four subshells, 4s, 4p, 4d, 4f. Like that's what I am doing. Second shell has 2s and 2p. Let us see whose energy is less. 2s means 2 plus 0, energy is 2. 2p means 2 plus 1, it is 3. So among 2s and 2p, which were expected to be in the same shell, second shell, 2s is of less energy, 2p is of relatively more energy. So like this, energy of orbitals must be calculated and remembered. Next, third shell has 3s, 3p, 3d. How many subshells? 3. And each subshell has several orbitals. 3s has only one orbital, 3p has 3 orbitals, 3d has 5 orbitals. 5 plus 3, 8 plus 1, 9 orbitals third shell has. So what are the energies of these orbitals? So 3s energy is 3 plus 0, it is 3. And 3p has 3 plus 1, 4 has energy. 3d energy is 3 plus 2, it is 5. Likewise, we can get a fourth shell which has 4 subshells, 4s, 4p, 4d, 4f. So energy of 4s, 4p, 4d, 4f. Let us calculate. 4s energy is 4 plus 0, it is 4. 4p is 4 plus 1, 5. 4d is 4 plus 2, 6, 4f is 4 plus 3, that is 7. In this way, starting from the nucleus, the corresponding orbital's energy can be calculated. See, now here one more point we have to notice. Degeneracy, already we discussed that. 2p subshell has how many orbitals? 3. px, py, pz. These 3 p orbitals, as n and l values are same for these 3 p orbitals, those 3 possess same energy. They are equal in energy and thus are called as degenerate orbitals. What are 2px, 2py, 2pz called as degenerate orbitals. Same way under 3p also, 3px, 3py, 3pz also called as degenerate. 4px, 4py, 4pz also degenerate. And apply the same concept for 3d. 3d has how many orbitals? 5 orbitals. dxy, 3dxy, 3dyz, 3dzx, 3dx square y square, 3dz square. Even these 5 also observed as of same energy. Of course, in higher classes, means in the same 11th and 12th classes only, in the higher topics, we are going to study about the variation of these energy of d orbitals with respect to the approaching species. But at present, you remember that 3d orbitals, 5 3d orbitals are of same energy as they possess same n and l value. Now, energy of 3d orbitals can be given as 5. All the 5d orbitals are of same energy. Now, our question is, among all orbitals, which orbital is of least energy? 1s is of least energy. Energy of 1s is less. Next, 2s. Next least energy, we have 2p and 3s, both are having same energy. Have you noticed? When different orbitals are with same energy, then the one with less principal quantum number must be considered as of lowest among them. So among 3s, principal quantum number is 3, 2p, principal quantum number is 2. These two are having same energy, then you have to give preference to the least principal quantum number, that is 2. So after 2s it is 2p, and then so energy of 1 is less than 2s less than 2p, and then after 2p next least energy orbital is 3s. Now after 3s we have energy 4 for 2 orbitals. Have you noticed? For 3p energy is 4, for 4s also energy is 4. So when energy is 4 for different orbitals, we have to give preference to least value of principal quantum number. This is 4 principal quantum number, this has 3 principal quantum number. So energy of 3p is less than 4s. Now among 4s, 3d is left. 3d has energy 5, 4p also has energy 5. Among 4p and 3d, now you can answer which has least energy. Even though their energy is observed as same, among them least energy can be assigned for the one with less principal quantum number. So after 4s, it is 3d less than 4p, so on. So this is how we can calculate energy of orbitals for other species. Whereas energy of orbitals in hydrogen atom can be given as 1s less than 2s equals to 2p, because there is no accommodation above 1s. 2s equals to 2p, 3s equals to 3p equals to 3d, less than 4s equals to 4p equals to 4d equals to 4f, so on. This is in case of hydrogen. But in practice, when more electrons are to be filled, energy of orbitals can be calculated in this way. This is for hydrogen atom, and that is for multi-electron species, right? So using this energy of orbitals, order of filling electrons in these orbitals was given by Aufbau principle. Aufbau principle. Aufbau principle means, Aufbau means to build up, building up. The meaning of Aufbau is building up. So it is while building up of an atom. What does Aufbau principle states? While building up of an atom, electrons occupy the orbital with least energy first. Electrons occupy the orbitals with the least energy. So which has least energy? 1s. Of course, these are subshells. Subshells are sub-energy levels, under which if any orbitals are available, degenerate orbitals, they have to be filled equally. Okay. Now, oneness total capacity is, total capacity or total accommodation is 2 electrons. S anywhere, S sub shell is 2 electrons, P sub shell is 6 electrons, 3 is again 2, P is 6, S is again 2, D is 10, this is 6. So the maximum capacity of a subshell, in the last class we studied, that also to be considered. Means first electron, suppose if a hydrogen is considered whose atomic number is 1, electron will enter the first least energy orbital, that is 1s. So its configuration can be given as 1s1. Right? Suppose helium whose atomic number is 2. Helium whose atomic number is 2. Its configuration can be given as, it's not helium 2, atomic number is 2. See, helium atomic number is 2. 2 electrons must be filled. Again start from least energy orbital 1s 2, because S can be filled with maximum 2 electrons. S subshell or S orbital. In orbital, any orbital can be filled with maximum 2 electrons. S subshell maximum capacity is 2 electrons. When it comes to lithium 3 electrons must be filled, among which 2 must be filled in the least energy orbital 1s. Next third electron will enter into the next low energy orbital, that is 2s. Next, beryllium atomic number is 4. Beryllium atomic number 4. So in beryllium 4 electrons, again start with 1s for any atom, 1s2. Next 2 electrons will be entering 2s2. 4 electrons are filled. When it comes to boron, atomic number is 5. Boron atomic number is 5. 5 electrons again start with the least energy orbital 1s, which can be filled with maximum 2 electrons. Next low energy is 2s, which can be filled with maximum 2 electrons. 4 already filled. Next 5th electron enters into 2p, that is 5th electron. So in this way, we can write the electronic configuration of elements using this energy sequence. Understood? Likewise, if you take carbon, suppose if we take a carbon whose electrons are 6 number of electrons, it is 1s2, 2s2, 2p can be 2p sublevel, 2p has 3p orbital, 3 orbitals, right? So each orbital can be accommodated with 2, 2 plus 2 plus 2. So a p subshell can be accommodated, this is subshell. Subshell total capacity. See, I am repeating the line. Subshell total capacity is in this way. Orbital, whatever the orbital, irrespective of its name, orbital, one single orbital can be accommodated with how many electrons? 2 electrons. There is no change in that. One orbital can be accommodated with always 2 electrons only. But subshell capacity is different. In the last class we observed this one. Now, subshell 2p subshell maximum capacity is 6. Why 6? 2px 2 electrons, 2py 2 electrons, 2pz 2 electrons. So we can fill this 2p up to 6 maximum. Already 2p1 is filled, this is 2p2. 2 plus 2 plus 2, 6 electrons. Nitrogen 7. 1s2, 2s2, 2p3. Oxygen 8. 1s2, 2s2, 2p4, 8 electrons. Fluorine 9. 1s2, 2s2, 2p5. Neon 10. 1s2, 2s2, 2p6. Finished. So the maximum capacity of a p sublevel is 6 electrons. It's filled. Now when it comes to sodium 11 electrons, 1s2, 2s2, 2p6, 10 electrons are filled. 11th electron will enter after 2p. What is the one with least energy? 3s. That 11th electron will enter into 3s1. So in this way, one should be in a position to write the electronic configuration of all elements in the periodic table. Yes, you have to write the electronic configuration. Why I am insisting you to write, there are some anomalies in heavier elements. This energy sequence is valid up to some atomic number. Above that, in heavier elements, when it comes to transition elements, as we move away from the nucleus, energy difference between the energy difference between the main energy levels will be negligible. That's why there are some anomalous electronic configurations also. To observe that, one has to write the electronic configurations first using this picture. Then they can observe the anomaly. Wherever variation is there, then they can easily notice. Instead of writing it first on your own, if you directly look at the textbook and remember, definitely after 1 or 2 classes you will forget that. So first you have to write the electronic configuration like for all 118 elements given in the table. At present, whatever the 118 elements given. It may be a tedious job, maximum 40 minutes it may take. Okay, if you spend 40 minutes for today, definitely for all these 2 years chemistry, you will be in safe job. You need not go here and there, or you need not take time to recap that electronic configuration. You do write the electronic configuration for all 118 elements. Sir, only few sequences you had given. Then how to write the electronic configuration for all heavier elements? I can give you one diagram given by Euler, using which you can easily write the electronic configuration. When it comes to this Smallness diagram, which shows or which gives an easy approach of increasing energy of orbitals, you know that first shell is has only one subshell, that is 1s. Second shell has 2s and 2p. Third shell has 3s, 3p, 3d subshells. Fourth one has 4s, 4p, 4d, 4f. Fifth shell has 5s, 5p, 5d and 5f. Even 5g is also there, but that much big atom with a higher atomic number is not discovered so far. That's why this is hypothetical. Next, 6s, 6p, 6d, 6f. After this, they are all hypothetical. See. Next, 7s, 7p, so on. I am stopping this because for the existing elements, it is enough if you fill till here. The existing elements will be finished. Like once again, for maximum capacity of S subshell. So these points are very important. Orbital means 2 electrons fixed, no change. S or P or D or F orbital. But subshell means you have to remember these points. For S subshell, it is 2, P subshell, it is 6, D subshell, maximum are 10, and F subshell, maximum electrons that can be filled are 14. Any, it may be 3D, 4D, 5D, 6D, etc. It may be 4F, 5F, 6F, any F. It may be 2P, 3P, 4P, 5P, any P or any P sublevel. 6 electrons only. Now let's come here. These are all subshells. S subshells, P subshells, D subshells, F subshells, so on. Now this is the direction. See the direction of arrow, 1s. After which you have to take a turn and again fill 2s. After that you have to take a turn, fill 2s. And after 2s, again take a turn, fill 2p and 3s. See the direction of arrow. Again after 3s, 4p and 3p and 4s. After 4s, you take a turn, 3d, 4p and 5s. Again 4d, 5p and 6s. Again 4f, 5d, 6p and 7s. And again 5f, 6d, 7p, so on. So if you follow this Smallness diagram, this is the running sequence. Direction also you have to should be very careful. Using this Smallness diagram, you can easily write electronic configuration of any heavier element. Of course, after writing the configuration, we will discuss all those anomalies also. Because of negligible variation in energy in heavier elements, there are some anomalies that also we are going to study. But before that, every student without fail must write the electronic configuration. It is tedious, I agree, it is tedious, but you have to write up to the whatever the 5F and 6D also that can be filled. Till that point you have to write. Up to 5F only we are going to fill the electrons. Okay, write it by taking a continuous pages, right? See, it is for your good sake only. It helps you like anything. If you are good at electronic configuration, means you are good at chemistry. Understood? So for that reason, everyone has to write this electronic configuration using Smallness diagram, and better you remember the sequence 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14. Like that, the sequence must be remembered in a continuous manner.